Hello friends, in today's class we are going to talk about segmentation. Welcome here and we are talking about segmentation and to be summarize what exactly the segmentation is, what we can say directly that segmentation is the user view of memory. Okay, user view or rather than programmer's view of memory. View of memory. So how programmer perceive the memory as. Okay, so here few points are there, theoretical points are there for this, that do user think memory as a linear array of bytes containing instruction and other containing data. Okay, so this is the, do we have this perspective? We have all of them. Okay, the entire memory is what, there is some part, there is an instruction and there is some part of we are having a data. Consider how you think a program when you're writing. You think a program as a main program, set of subroutine, function and modules. Okay, so whenever we write a program, what program basically consists of? Your program basically consists of you have a main program. Okay, main program, then you have a subroutines. You have procedures. And you have a functions, or you have a function, or you have a module. Okay, so there is a modular structure of the program, and program is also consist of what different parts. Okay, different parts program is consist of. Okay, so it says that that program is divided into a program symbol table, function, sqrt, main program. Now without getting the address of memory this element occupy. Okay, so program is divided or written in a modular manner. Okay, modular manner, modularity is a modular manner. It is written that there are different parts of the programs. There can be a main program, then we can have a symbol table, then we have a, let's say, procedure sqrt. Okay, so that way. And you're not concerned whether the symbol table store before or after the sqrt function. Okay, each of this segment is a variable length. Okay, and yes, if you talk about what is the length of the program, okay, what is the length of program, then we can say that each of this program is of variable length. They are not of the fixed length. And who is first, who is second, we are not concerned with, but yes, this is sure that they may not be of the same length. The length is intrinsically defined by the purpose of segment in this purpose. Okay, element within the segment is identified the offset. Okay, so now each of this segment is of variable length, and the length is intrinsically defined by the purpose of segment in the program. Okay, so we call that a program segment. Okay, and that program segment is idea that is taken into the segmentation of memory also. Variable length, user perspective, segmentation of it. Element within a segment is identify the offset from the beginning of the segment. So as offset is now not a new term. Offset, we have seen the D term that we have already seen. The offset within the page, we are talking about offset within the segment. The first statement of the program, the 17th entry in the symbol table, the 5th instruction of the sqrt function, and so on from the beginning. So what is exactly the segmentation? This is the definition, that was the overview. Segmentation is a memory management scheme that support user view of memory. Okay, so how the user view the memory, like I've already told you that there is a main function, and then there can be user, then there can be sqrt function. Okay, and then there is a function to print output function, something like that. Huh? Each okay, logical space of a logical address space is a collection of a segment. Okay, each segment has a name and a length. The address specify the segment name and offset within the segment. Okay, so each segment has a name and the length, and address specify what does the address specify? Segment name and offset within segment name and offset within the segment name and offset within the segment. Segment name and an offset. Contrast this scheme with the paging scheme, in which user specified only a single address, which is partitioned by the hardware into page number and an offset, all invisible to the programmer. Okay, now this is the one key difference about the segmentation and paging, that it's not like a paging scheme, okay, in which the user specified only a single address which is partitioned by the hardware. Okay, user is only generating what? It's a logical address, it has been generated, and that is taken care by entirely by the hardware. What is page number, what is the offset, that user is not concerned of. Okay, so that is what is saying, that is the difference between this segmentation and this paging scheme, that in which user specified single address which is partitioned by the hardware into page number and offset, all invisible to the programmer. Okay, so programmer is not simply concerned of this. For simplicity of implementation, segment are numbered as referred as segment number and rather than by segment name, and logical addresses consist of two tuples. So now we have a no segment name, rather than we have a segment number and offset within the segment. Okay, so I think you understand this point. One of the important point here in this case is this part where it says that a user or in this paging scheme is entirely implemented by the hardware and it is totally invisible to the user. Okay, so main memory management scheme support the user view of the memory. Program is a collection of segment. Logical segment can be main program, procedure, function, method, object, local and global variable, common block, stack, symbol table, array. So these all can be the segment, and we can have different segment over here. Okay, so that is a logical address space and it is divided into the different segment. Okay, so there is user space and here 1 2 3 4, and it can be of variable length. Now segmentation architecture, as we have already seen that there will be segment number and the offset value. There is a segment table maps to a two-dimensional physical address, and each entry has a base and as well as the limit. Okay, so we have a logical address space consists of segment number and the offset value. The logical address space that was divided into page number and D, now we are dividing into segment number and D, and we have a segment table. Like a page table, we have a segment table. So what we are having in a segment table is the base, register, base and limit value. Okay, so page table base is a base table, segment table base register point to the segment table location in the memory, and segment table length register indicate the limit. Okay, legal is what? If it is less than the limit. Okay, if it is less than the limit, SLTR, segment table length register, is less than limit, then it is a legal one. Protection, each entry in the segment table is associated with validation bit. Validation bit 0 is an illegal segment, read write, and protection bit is another access control is also there. Okay, so protection bit is associated with the segment codes sharing at segment levels. In the segment varying the length, memory is dynamic storage allocation problem, and segmentation example shown in the following diagram. Okay, so this is the exact diagram that we have P and D. So we have a S and D. The segment table, it will go. It will say the limit. It will go to the limit. If it is say no, then trap. Otherwise yes, go to the base. Take the value. So this. So first, what we do, we will go to the segment number, and then we'll check the limit and see the offset value. Offset value we'll check. Okay, so that is all of for this segment, and the basic idea here is this: to support the user view of memory, and it is like paging is invisible to the programmer. Here it supports user view of memory. Okay, the logical address space is now programmer can think that the logical address space is divided into different segment. These can be segment, a user view of program, logical view of segment. Okay, so that is same as the user view of program. That is the logical view of segment. Okay, so let's discuss this problem. A certain computer system has a segmented paging architecture. Okay, so we have a segmented paging architecture for virtual memory. The memory is byte addressable. Both virtual and physical address are 2 to the power 16 bytes each. 2 to the power 16 bytes each. The virtual address space is divided into 8 non-overlapping equal size segment. 8 non-overlapping equal size segment. The MMU is a hardware segment table, and each entry of which contain the physical address of the page table for the segment. Okay, so this MMU is a hardware segment table, and each entry contain the physical address of the page table, for the segment. Okay, so remember here, okay, physical address of page table of the segment. Page table stored in the memory consists of 2 byte page table entry. Let's come back here. What is the minimum page size? What is the minimum page size? We have to find minimum page size in bytes, so that page table of a segment requires at most 1 page to store. Okay, so page table for a segment, page table for a segment. Assume that the size of the page, okay, so size of the, okay, so now what should be the page size? It's not given to us, not given to us. Okay, so now here one segment size, so there are 8, 2 to the power 16 is the total size virtual memory, and there are 8 segments are there, so that will become what? 2 to the power 16 divided by 2 to the power 3. One segment size will be 2 to the power 13. Okay, what should be the minimum page size in bytes? So the page table for a segment. Okay, suppose I can assume here, suppose page size is 2 to the power k byte. Okay, so number of pages will be what? Number of pages in this case is equal to what? 2 to the power 13 divided by 2 to the power k. You'll agree with me on this? 2 to the power 13 minus k. This is the total number of pages. Okay, and page table for a segment will have these 2 to the power 13 minus k entries will be there in that case. Okay, because for each page there will be 1 entry for that segment. Hence, with the given condition, what I can say, 2 to the power 13 minus k into each size is what? 2 byte, should be equal to what? It should be equal to 2 to the power k. These many entries are there, and each entry is of size what? 2 byte page table entry. They should be equal to this byte, right? So now this will become what? 2 to the power 14 minus k is equal to 2 to the power k, and what? 14 minus k is equal to k, and this implies that k will be equal to what? 2k, k will be equal to 7, and I can say that page size is equal to 2 to the power 7 byte, 128 byte. Okay, so there will be 128 byte pages. So I hope you agree with me on this. B part is, now suppose that page size is 500 byte. Okay, now we're changing it. Page size, again it is changing this page size value. Page size is equal to 512 bytes. It is proposed to provide a TLB. It is proposed to provide a TLB, translation location buffer, for speeding up the translation. Okay, TLB is there. The proposed TLB is capable of storing page table entry for 16 referenced virtual pages. 16 referenced virtual pages. So this can store only 16 entries. 16 entries it can refer. In a fast cache, that will be a direct mapping. Okay, so now this is a direct mapping. what is the number of what is the number of tag bits that will be needed to be associated with each cache entry? Okay, tag bits we need to find. Okay, tag bits. So this is something related to the cache mapping, tag bits. Okay, now here we have this virtual address space is equal to how many bits here? 2 to the power 16. So there are 16 bits are there. 16 bits are there, and this will be divided into two part, page number part, and page offset part. Okay, so now here we have say out of 16 bit 9 bits because memory, I think it is said that memory is byte addressable. If it is not, then we can assume, because nothing is mentioned here. Okay, it is not mentioned. Okay, 9 bits. So what we are remaining here in this case is 16 minus 9, so that we are remain with here 7 bits. So this 7 bits will be go for this TLB comparison. Okay, that this diagram we have already seen, TLB comparison, something like this. Okay, so parallel search, associative search that we call. Okay, so now here this 7 bit will be divided into direct mapping. A direct mapping have only two fields. One is your tag and another is your block offset. So means a TLB entry offset. We can say TLB entry offset. So how many entries are there in this case? The number of entries in this case is, how many entries are there? Only 4 bits, 16 entries. So 4 bits required here. So remaining is what? 3 bit. So 3 bits will be used for the tag, 3-bit tag comparison. Okay, so only 3 bit required for the tag comparison. Okay, so last one is this. Okay, so now here the last part of this question is this, and we can say that here, assume that each page table entry consists of one valid 3 bits. Each page table entry, PTE it is talking, page table entry it is talking about, which is 2 byte wide, 2 byte in size. Okay, assume that each page table entry contains one valid bit, one valid, 3 bits for the protection, 3 bits for protection, and one dirty bit. How many bits are available for page table entry for storing the aging information of the page? Aging information. Assume that page size is 9 byte. So now PT entries consist of what? Now this is a simple problem. PT entry, this entry is total 16 bits wide. Okay, 16 bits entries are there in this case, and we have what? Frame number. Frame number. We have what? One valid. We have what? 3 bit for the protection access control, one dirty bit, and we have aging information. Okay, now frame number will be what will be the size of the frame number? So here in this case will be 9 bits. This will be 9 bits, and here one dirty, so one dirty, 3 bits for valid, invalid, and 1. Okay, so 9 plus 1, 10, 10 plus 4, 14. 14 bits are used here in this case. Okay, 14 bits we have already used. Okay, so if we have already used the 14 bits, then we are left with how many bits? Only 2 bits we are left with. Okay, so one valid, 3 for the protection, one valid, 3 for protection, one dirty, that is 4, and 9 bit is for this. So that total sum up to 14, and total size is 16 bits. So we'll only 2 bit left for the aging, 2 bits for this, I think. Okay, so that is a very big long question, but I hope you understand this particular problem. Okay, so that's all for this discussion. Thank you.